Okay, folks, continuing along. So we're going to discuss gas phase FTIR spectroscopy, or sometimes that's referred to rotational vibrational spectroscopy. And with that is going to come the very famous P, Q, and R branches. So let's go for it. So this rotational vibrational spectroscopy is primarily dealing with vibrational spectroscopy of gases. So something interesting happens when we start thinking about the vibration of gas phase molecules that are free to rotate. And the classic picture that's used to describe this is the quantized ice skater. So imagine we've got an ice skater out here with their arms elongated and they're spinning at a certain frequency. I think we all know commonly from either observing this or doing it ourselves, when they bring their arms in, they will increase their angular momentum. And in the case of molecules, right, that vibration of elongating the bond and compressing the bond will intimately couple with those rotational moments, as the picture is shown here. So we recognize in a normal FTIR spectrum, we're really just probing the fundamental transition, right, from 0 to 1 and vice versa. However, these gas molecules will inadvertently excite the rotational levels as well. So we think of this in terms of the nu and j quantum numbers. So we'll call up a new function here, s, and that's s tilde, right? We're dealing with the wave numbers. And now notice that's going to be a function of g, which we just described in the previous video, and f, which we described in Learning Goal 5. And relying on those solutions, and in this case, ignoring the anharmonicity contribution, right? We've got the nu plus 1/2 times nu, so this is our vibrational constant. And then we've got the j times j plus 1 times b tilde, which is our rotational constant. So we need to consider both of those in the gas phase vibrational spectroscopy. So now those are divided up into three things: the P branch, the Q branch, and the R branch. So all of these branches deal with nu plus 1 from nu. Okay, so the quantum number nu changes by 1. So we'll note that for all of these. And because all of our molecules exist primarily in the ground vibrational state of 0, these really all are probing from 1 to 0 or 0 to 1, depending on how we think about it. So now if we look at the P branch here and we zoom into this, so the P branch here is on the left side of this document. Here, this is all the ground vibrational state. So we'll say that's my ground state and all of the various rotation levels within the ground state. And here is my first vibrational excited state corresponding to nu equals 1. So now you can see if I take a peek at this first line here, it is starting at a j value of 1 and going up to a j value of 0. So now if I look at the next one, it's starting at a j value of 2 and going up to a j value of 1. So that means the P branch has a delta J of -1 relative to the ground state. So I'm going to skip over the Q branch and go to the R branch, and we'll talk about what we observed there. So we can see with the R branch, it starts at a J value of 0 and goes up to 1. The next line starts at a J value of 1 and then goes up to 2, etc. So the R branch corresponds to a J transition of +1 relative to the ground state. And then now finally, hopefully what you can see from the Q branch is it goes from J equals 0 to J equals 0. Then we have another one that goes from J equals 1 to J equals 1, and so forth. So the Q branch corresponds to delta J equals 0. And for most molecules, this is a forbidden transition because with no net change in angular momentum, nothing can compensate the absorption of that photon. Now, there are some molecules in which a Q branch is observed, and this is typically those that have electric angular momentum at their ground state. So typically for radicals. So things like NO will give a Q branch, but things like CO, carbon monoxide, will not give a Q branch. So I'll write that down on the next slide where I've got a little bit more room. So now, putting all of this together, we can come up with some predictive equations to describe this. So for the P branch, I'm going to write that as nu tilde P, which equals delta S, right? Remember, a spectroscopic transition is a change in energy levels. And that's going to be from nu plus 1 and J minus 1. And that means the, expanding on those, the S final state will be given as the nu plus 1, J minus 1, and then minus our S initial, so I'm going to write S final right there, and S initial for the delta. That will just be given as nu and J. So if we expand out on those, we get the following. So if you recall, my S function, right, was, we can locate it right there. There it is, nu plus 1/2 times nu tilde plus J times J plus 1 times B tilde. So collecting all of that, my S final state is going to go as the following. It's going to be nu plus 1 plus 1/2 all times nu tilde plus, and then now it would be J times J plus 1, but I've got to remember that my J is really J minus 1. So that's going to be J minus 1 times the quantity J minus 1 plus 1 all times B tilde. So that was my S final. Now minus my S initial is, of course, going to be just nu plus 1/2 times nu tilde plus J times J plus 1 times B tilde. And if I go through and do all of the algebra, I'm just going to shortcut through that and get us straight to it here. Our new P branch will be the following. It will go as the quantity nu minus 2J times B. So there is going to be some significance there that we shall see. So for example, let's suppose for my first J value, J equals 0. So the way that this goes, this J value corresponds to the initial value. So the initial value then for this transition would be J equals 1, right? That's the only way I can get a delta J of -1. So now from this, I'll get a series of lines that go as the following. It will be nu tilde minus 2 times B tilde for J equals 1. My next line will be nu tilde minus 4 times B, and etc. Hopefully you can see where this is going. This is going to give us the same 2 times B dependence spacing between each peak, which is kind of cool that it works out that way. Okay, so now if we were to go to do the same thing with the Q branch, let's get all of that put together. We know that that's going to be delta S of nu plus 1 times J. So because no J values change there, the only thing that changes are the nu values. So now that means my S final state is nu plus 1 and J minus my S initial state, which is just nu and J. So when I plug all of those in, because J is not changing, hopefully what you recognize is the Q branch just equals the vibrational constant. And so in the case of a liquid or solid that doesn't display a rotational vibrational spectrum, the Q branch is the peak of that vibration. Okay. But again, we said that this was forbidden for most molecules because there is no change in angular momentum. However, if something has intrinsic electric angular momentum from its electronic structure, then it will exhibit a Q branch. So for example, NO being a radical has a Q branch, but CO not being a radical does not display a Q branch. So other common molecules that don't display Q branches are things like HCl. So this is our classic rigid rotor. So that does not have a Q branch. Okay, and if we go do the same exercise for our R branch, I'll just cut straight to the chase. We get the following. So it ends up being 2 times B tilde all times J plus 1. And remember, that's our lower J value. And for the R branch, because delta J equals plus 1, the first J value will be 0, right? Oh, so I forgot one thing. So then that's plus nu tilde. Apologies. So let's box those off. So here is this one. So now with the R branch, the first J value is J0. So we will see a series of lines that look like the following. 2 times B plus nu for J equals 0. For J equals 1, that's going to be 4 times B plus nu tilde. For J equals 2, that's going to be 6 times B plus nu. So we see the exact same pattern of 2B spacings, but now with the R branch, they're going plus the wave number, so these are going out to larger wave number values. And for the P branch, these are being subtracted, so they're going out to smaller wave number values. So let's take a look at what some real spectra look like. And these are just fantastic to look at. I love looking at these spectra. So these were recorded from some Chem students using the Schlenk line. And so these are gas phase samples and low pressure gas phase samples. So we minimize the amount of peak width broadening. So now based on what we just talked about, we recognize right here in this gap, there should be a Q branch, but it's missing because HCl has, that's forbidden for HCl. So now when we go in this figure to the left of that to increasing wave number values, that is the R branch. And then on this side here to decreasing wave number values, that is the P branch. And also, if you have a really keen eye, you might notice these peaks are spaced apart evenly, kind of. We'll talk about that in more detail soon. And they are spaced by approximately every 2 times B. And the P branch to R branch is spaced by 4 times B, which is pretty cool. And now what you'll also notice, if I were to like zoom in on any of these peaks here, I would actually find that there's a doublet going on in there. So why is there a doublet? Well, as it turns out, chlorine has a reasonable population of isotopes. And by reasonable population, I mean like compared to carbon, that's 99% carbon 12 to 1% carbon 13. Chlorine is like 75% 35 and 25% 37. So the taller peak actually corresponds to H35Cl, and the smaller peak corresponds to H37Cl. And they are separated because they will have different angular momentums and thus different force constants due to the different masses of the isotopes, which is pretty cool. So now down below we have DCl, and I'll also highlight the Q branch here. And you can see the Q branch for HCl occurs around close to 2900, but the Q branch for DCl would occur around 2100. So that difference is related to the deuterium versus the hydrogen. And you'll also notice there are doublet peaks in here as well, and they're actually much more resolved. And they're much more resolved because of the differences in mass between a hydrogen and a 35 chlorine and a deuterium and a 35 chlorine. So once again, this would be D35Cl, and this one would be D37Cl. So we can learn all kinds of fantastic information about these spectra, and we're going to digest these in a lot more detail in our Spec 2 assignment. So just looking at a couple more of these, here is HBr, so looks very similar to HCl and DCl. However, we don't see any doublets there. And that's because now the mass differences between HBr, so if you think about it, right, like the D35 and D37 showed a significant difference. The H35 and the H37 showed an even smaller difference. And now bromine has isotopes at 79 and 81. So these have an even lesser, or I should say they have an even bigger difference, right, is the right way to say that. So we don't see their isotopes resolved as much. And really that's related to the fact that the bromine is so much more massive than the hydrogen that it really is looking like a single mass attached to a wall. So this HBr follows this model really, really well. So differences in isotopes for this model are minute, whereas differences in isotopes for the chlorine halogen, or the HCl, right, were much more prominent because the mass of the chlorine is so much less than the mass of the bromine. And then finally, here's a look at carbon monoxide. So once again, we can see a missing Q branch right there. And what we should also notice, the peaks are packed much more tightly together. And that's because CO has a much smaller dipole moment than HBr or HCl, thus giving it a much smaller rotational constant. So the B constant for CO is much less than the B constant for HCl, for example, and that makes the peaks much more closer together. What I also want to point out here is we get some great statistical mechanics from this. So we can see here there's a Boltzmann population of rotational states, right? So if we fit a curve through those peak energies, we get mirror image Boltzmann distributions because there will be a Boltzmann population of rotational states. All right, that's good enough. We will explore this in a lot more detail in the computer lab. I'll see you then, folks.